So in the previous lecture, we saw how we could use the phase-1 linear program to find a feasible solution to a linear program that we would like to solve. What we're going to be doing in today's lecture is we're going to talk about how we can start simplex method from that feasible solution for the linear program that we would like to solve, and then apply the iterations of simplex method to get to the optimal solution for the linear program that we would like to solve. So that's the first thing we're going to do. Phase-1 linear program gives a feasible solution to a linear program that we would like to solve. Today, we're going to see how we can start simplex method from that feasible solution to the linear program that we would like to solve, and apply iterations of the simplex method to get to the optimal solution for the linear program that we would like to solve. So that's the first thing we're going to do today. And the second thing we're going to do today is going to be the following. All the linear programs that we solved so far through the simplex method had less than or equal to constraints and decision variables that are restricted to be non-negative. But in general, we may have linear programs with greater than or equal to constraints, equality constraints. We may have the linear programs where decision variables are restricted to be non-negative, non-positive. We may have some decision variables that are allowed to be both positive and negative. So we're going to look at how we can take more general types of linear programs and still be able to solve them through the simplex method. That's going to be the second thing we're going to be talking about, how I can deal with more general linear programs within the context of the simplex method. Okay, first things first, let's talk about once I use the phase-1 linear program to find a feasible solution to a linear program that I would like to solve. How can I start simplex method from that feasible solution and apply iterations of the simplex method to get to the optimal solution of the linear program that I would like to solve? So in order to do that, we're going to roll back and go over some of the ideas that we talked in the previous lecture, because continuity is always good. Some repetition and some continuity is always good. So let's try to remind ourselves how the phase-1 linear program worked. Let's try to remind ourselves how the phase-1 linear program worked to find a feasible solution to a linear program that we would like to solve. Let's take our example. Let's say that we would like to solve a linear program, maximize x1 plus x2, subject to the constraint x1 minus 3x2 is less than or equal to minus 28, x2 is less than or equal to 20, minus x1 minus x2 is less than or equal to minus 24. My decision variables are non-negative. So I would like to solve this linear problem, okay? All right, so then let's try to apply the simplex method as we know. So the first thing we're going to do is we're going to express all of the inequality constraints in our simplex method as equality constraints by using the slack variables. Keep the same objective function, maximize x1 plus x2, and stuff the left-hand side of the first constraint with a slack of W1. Second constraint with a slack of W2. And the third constraint with a slack of W3. And all of my decision variables, including the slack variables, are non-negative. So this is how we get started if I'm going to solve this linear program. We express all of the constraints in my linear program as equality constraints. Okay, good. What's next? What's next? What's next? The next thing we do is we express the linear program that we would like to solve with equality constraints as a system of linear equations. That's how we apply the simplex method. Maximize the objective function. There we go. This is the system of linear equations corresponding to the linear program that we would like to solve. So then if you want to get the simplex method going, what is the solution that we read from this system of linear equations? Our basic variables are W1, W2, W3. So the solution that we read is W1 is minus 28, W2 is 20, W3 is minus 24, x1 and x2 are 0. If x1 and x2 are 0, z is going to be equal to 0. So now this is, the simplex method that we applied as of 2 lectures ago, as of 3 lectures ago. But the immediate difficulty that we run into is that once we sort of initialize the simplex method like this to solve this linear program, the initial solution that we have here is x1 and x2 are equal to 0. Is this solution feasible to the linear program that we would like to solve? X1 and x2 is 0, 0 plus 0 is 0. 0 is not less than or equal to minus 28. 0 is not less than or equal to minus 28. So then this solution that we immediately read from the initial system of equations is not feasible to the linear program that we would like to solve. Okay, and that's an immediate issue because the simplex method starts from a feasible solution to the linear program that we would like to solve, and then we apply row operations to get to better and better and better feasible solutions that give us better and better and better objective values. But right now, when I'm solving this linear program, I don't even have an initial feasible solution for the simplex to start with. Okay? So that's why we developed this phase-1 linear program to find an initial feasible solution for the linear program that I would like to solve. And now we can apply the simplex method from that, starting from that initial feasible solution. Okay, so if you apply the simplex method business as usual, the initial solution that we obtain here is not even feasible to the linear program that we would like to solve. This solution is not feasible to the LP we want to solve. So the simplex method cannot start from the solution. Okay, so then the question is, how can I find a feasible solution to this linear program so that I can start the simplex method from that feasible solution, then do row operations to get to better and better and better feasible solutions? How can I find a feasible solution to this linear program that I would like to solve? In order to do that, we devised this phase-1 linear program. What did the phase-1 linear program look like? In order to do that, let me just write in this corner. It turns out, let's say, to find a feasible solution to the linear program that we would like to solve, we can solve yet another linear program. Find a feasible solution for the LP we want to solve. It turns out we can solve another linear program. And what did that linear program look like? Find a feasible solution to the linear program that we would like to solve. It turns out I can solve another linear program. Let's remind ourselves what that linear program looked like. Let's copy the constraints of the linear program that I would like to solve as before. 3x1, x1 minus 3x2 less than or equal to minus 28. x1 minus 3x2 is less than or equal to minus 28. What else? x2 is less than or equal to 20. Good. What else? Minus x2. What else? Minus x2, minus x, minus x1 minus x2 is less than or equal to minus 24, and x's are non-negative. Good. So I want to devise a linear program that is going to allow us to find a feasible solution to this linear program. Here's what we did. We added a additional decision variable u to the right-hand side of each one of these constraints. And this u decision variable was a non-negative decision variable. And in the objective function, we minimize this u decision variable. Okay, good. And we said this is the linear program that is going to allow us to find a feasible solution to this linear program. This is the linear program that is going to allow us to find a feasible solution to this linear program that I would like to solve. Okay, how did this linear program allow us to find a feasible solution to the original linear program that I would like to solve? Here's the idea. In the objective function of this linear program, I'm minimizing u, and u is greater than or equal to 0. So I'm pushing u as low as possible. If at all possible, in the optimal solution of this linear program, I would like to push u as low as possible all the way down to 0. If I solve this linear program And at the optimal solution of this linear program, if the value of the decision variable takes value 0, if at the optimal solution of this linear program, the value of decision variable takes value 0, u's are 0, then the values of the corresponding x variables at the optimal solution is going to be feasible to the linear program that I would like to solve. They're the same constraints. Okay, let's say it again. In this linear program, I'm minimizing the objective function, just u, and use a decision variable greater or equal to 0. So if at all possible, I'm going to try to push u all the way down to the 0. That's the best I can do. So I solve this linear program. If at the optimal solution to this linear program, I'm able to push u variable all the way down to the 0, u's are 0, u's are 0, then the values of the x's at the optimal solution to this linear program, if you compare these two constraints, are going to be feasible to the original linear program that I would like to solve. Okay? On the other hand, if you solve this linear program, and at the optimal solution to this linear program, the value of decision variable u is strictly positive. So in this case, no matter what I did, I couldn't push u all the way down to the 0 while finding the x's, corresponding x's that satisfy these constraints. Then it means that the original linear program I'm trying to solve has no feasible solutions. Okay, so that is how we're going to use this linear program to find a initial feasible solution, to find a feasible solution to the original linear program that we would like to solve. And this linear program that we concocted has a name. It's called the Phase-1 linear program. Phase-1 linear program. It's called the Phase-1 linear program because this is the linear program that we solve to find a feasible solution to the linear program that we actually want to solve. And after we get a feasible solution to the linear program that we would like to solve, in phase 2, we apply the iterations of simplex method to get to the optimal solution to the linear program that we would like to solve. That's why this problem is called the Phase-1 linear program. Okay, so now let's try to sort of write down and solidify the observations that we did. The first one is, this phase-1 linear program is always feasible. There is no question of feasibility of the phase-1 linear program. Why is that? For example, if I said u is equal to 28, if I said u is equal to 28, and if I said x is all to be 0, that would be a feasible solution to the phase-1 linear program. 0 is less than or equal to minus 28 plus 28. 0 is less than or equal to 0. 0 is less than or equal to 20 plus 28. 0 is less than or equal to 48. 0, 0, 0 is less than or equal to minus 24 plus 28. So 0 is less than or equal to 4. And x1 is 0, x2 is 0, and u is 28. Both all are non-negative. So this phase-1 linear program is always feasible. Let's put it over here. Phase-1 LP is always feasible. Set u equals 28, x1 equals 0, x2 equals 0 to get a feasible solution. Great. So cool. Phase-1 LP is always feasible. There's no question of feasibility for the phase-1 LP. But the observations we made were the following. In the phase-1 LP, I'm pushing u as low as possible, and u is a decision variable that is greater than or equal to 0. So if at all possible, I'm going to push u all the way down to 0. That is the best thing I can do. If I solve the phase-1 linear program, and if at the optimal solution to phase-1 linear program, the decision variable u at the optimal solution to phase-1 linear program takes exactly the value 0, then the values of the x variables at the optimal solution to phase-1 linear program, if you compare these two sets of constraints, they're going to satisfy the constraints of the original linear program that I would like to solve. I solve the phase-1 linear program. If at the optimal solution to phase-1 linear program, if I'm able to push u all the way down to 0, the values of the x's in the optimal solution to phase-1 linear program, they're going to satisfy the constraints of the original LP that I would like to solve. Okay. On the other hand, if I solve the phase-1 linear program, and no matter how hard I push, I cannot push u all the way down to 0. If at the optimal solution to phase-1 linear program, the value of u is strictly greater than 0, then it means that I couldn't find u equal to 0 while finding x's that satisfies all of these constraints, which means that the original linear program that I would like to solve does not have any feasible solution. Let's write that observation. If the optimal solution x1, x2, u, and let me put stars here. if the optimal solution x1, x2 star, u star of the phase 1 LP has u exactly equal to 0, then what do we have? This optimal solution has to satisfy all of the constraints in the phase 1 LP. So let's write those constraints down. X1 star minus 3x2 star plus, oh, there is no plus, less than or equal to minus 28 plus u star. X2 star is less than or equal to 20 plus u star. Minus x1 star minus x2 star is less than or equal to minus 24 plus u star. And x1 star is greater or equal to 0, x2 star is greater or equal to 0. If at the optimal solution to phase 1 linear program, the decision variable u takes exactly the value 0, so this is 0, this is 0, this is 0, then the values of the x's, these are all zeros, then the values of the x's at the optimal solution to phase 1 linear program, they satisfy all of the constraints in my original linear program, so they're a feasible solution to the original linear program that I would like to solve. So x1 star, x2 star is a feasible solution to the original LP we want to solve. If, on the other hand, we solve the phase 1 linear program and at the optimal solution, the value of the decision variable u is strictly greater than 0, then there's no way I could push u. There's no way I could push u all the way down to 0 and find a corresponding x's that satisfies these constraints, which means that the original linear program that I would like to solve does not have a feasible solution. If the optimal solution x1 star, x2 star, u star of the phase 1 LP has u strictly greater than 0, then the original LP we would like to solve then the original LP we want to solve has no feasible solutions. It's infeasible. Good. So then the key is, if I want to get a feasible solution to this linear program that I would like to solve the phase 1 linear program. If at the optimal solution to the phase 1 linear program, u decision variable takes value 0, then the corresponding values of the x decision variables at the optimal solution is going to give me a feasible solution to the original linear program that I would like to solve. So now let's go ahead and solve the phase 1 linear program to get a feasible solution to the original linear program that I would like to solve. Let's write the system of equations that we need to solve the phase 1 linear program. Let me start with the constraints. x1 minus 3x2. Add the slack for the first constraint, w1. Okay. So that this inequality constraint becomes n. So I'm solving the phase 1 linear program to get a feasible solution to the original LP that I would like to solve. So let's go ahead and solve the phase 1 linear program. To get it, let's solve the phase 1 linear program. And if u star equals if u star equals 0 at the optimal solution to phase 1 linear program, I'm going to get a feasible solution to the original LP that I would like to solve. Okay, so now we're solving the phase 1 linear program. Here is the system of linear equations that I need to solve the phase 1 linear program. Put in the slack here, x1 minus 3x2 plus w1 equals, when I add the slack here, equals minus 28 plus u. Pull the u variable to the left-hand side, so it's going to read as minus u equals minus 28. This is the equality version of this constraint when I add the slack and pull the u variable to the left-hand side. Let's do the same game on the second constraint, x2 plus w2, so that this becomes an equality constraint. Pull u to the other side with a negative sign, equals 20, minus x1 minus x2 plus w3 equals minus 24 plus u. Pull u to the other side, minus 24. And in the objective function, we're minimizing u. In the objective function, we're minimizing u. Okay, so this is how we get started to solve the phase 1 linear program. Good. So let's apply the simplex method as we know it to solve the phase 1 linear program. This is the basic variables that we read. W1 equals minus 28, W2 equals 20, W3 equals minus 24, x1, x2 are x1, x2, and u are 0. These are non-basic. x1, x2, and u are 0. Those are non-basic. If u is 0, the value of the variable z has to be 0 as well to satisfy the first equality. Good. But now I run into an issue, right? As we said in the last lecture. I'm trying to solve the phase 1 linear program. Let's look at the first solution that we obtain when we're trying to phase 1 linear program. Is this solution feasible to the phase 1 linear program? x1, x2, and u's are all 0. 0 plus 0, that's a 0. Minus 28 plus u, 0, that's a minus 28. 0 is not less than or equal to minus 28. So this solution is not feasible to the phase 1 linear program. So now I'm a little bit scared because I feel like, oh my goodness, I'm trying to solve the phase 1 linear program, but I cannot even get a feasible solution for the simplex method to solve even just the phase 1 linear program. So I cannot get the simplex method started to solve even the phase 1 linear program. I'm a little bit worrying, I'm a little bit panicking. But it turns out that there is a simple special door operations that we do to get a quick initial to get a quick feasible solution to the phase 1 linear program. And let's remind ourselves that trick row operation that we need to do. All right, so let's write this. This solution is not feasible to phase 1 linear program. Okay. To get a feasible solution to the phase 1 linear program, we said there's a trick row operation that we need to do. And that was what? We take the constraint with the most negative right-hand side, add it to the objective function row, and subtract from every other constraint row. That immediately gives us a feasible solution to the phase 1 linear program that we can get started on and then apply the simplex method to get to the optimal solution to the phase 1 linear program. To get a feasible solution to phase 1 linear program, do one special row operation. Take the constraint row with the most negative right-hand side, add it to the objective function row, and subtract it from every other constraint row. Take the constraint row with most negative right-hand side, add it to objective function row, and subtract from all other constraint rows. So this is a special row operation. This is a trick. Somebody teaches you how to do this trick and you make the trick your own, but this is not a trick that you could figure out on your own. So this is a trick. And I'm going to call it trick number 1 because in today's lecture, we're going to see 2 other tricks. Okay. So when we're solving the phase 1 linear program, to get a feasible solution to the phase 1 linear program, the system of equations that we immediately start with does not give us a feasible solution to the phase 1 linear program, but there is one trick row operation that we do to get a quick feasible solution to the phase 1 linear program. Take the constraint with the most negative right-hand side, subtract it from every other constraint row, add it to the objective function row. Let's do those row operations and see what it gets us. Take this row, add it to the objective function row. x1, add it over here, minus 3x2 plus w1. No w2, no w2, no w2, no w3. Minus u plus u becomes 0u. On the right-hand side, we have z plus minus 27 added on top of that. Z minus 28. Z minus 28. Good. Then we're going to take the first row, multiply it by -1, add it to the second constraint row. x1 times -1 is -x1 plus 0x1 minus x1. Minus 3x2 times -1 is 3x2 plus another x2, 4x2. W1 times -1 is minus W1 and no W1 minus W1. No W2 plus another W2, W2. No W3, no W3, no W3. Minus u times -1 is plus u, minus another u, 0u. And on the right-hand side, minus 28 times -1 is plus 28, plus another 20, 48. Take the first constraint row, multiply by -1, add it to the last constraint row. x1 times -1 is minus x1, minus another x1, minus 2x1. Minus 3x2 times -1 is plus 3x2, minus another x2, plus 2x2. W1 times -1 is minus W1 plus 0 W1 minus W1. No W2, no W2, no W2. 0 W3 times -1 is 0 W3 plus another W3, W3. And lastly, minus u times -1 is plus u minus another u, 0u. What do we got on the right-hand side? Minus 28 times -1 is plus 28 minus the 24, 4 on the right-hand side. And I want to identify u as a basic variable, just so that u appears with a coefficient of 1 here. Let's take this row, multiply by -1, so that u looks like a basic variable. Minus x1 plus 3x2 minus w1 plus u equals 28. Good. What is the solution we read? What is the solution we read from this to this system of linear equations? What are our basic variables? What are our non-basic variables? Our basic variables u, w2, w3. U is equal to 28. W2 is equal to 48. W3 is equal to 4. X1, X2, and W1 are 0. X1, X2, and W1 are 0. Z has to be 28. Is this solution feasible to the phase 1 linear program? X1 and X2 are 0. U is equal to 28. U is 28. Minus 28 plus 28 is 0. 0, 0. 0 is less than or equal to 0. U is 28. 20 plus 28 is 48. X2 is 0. 0 is less than or equal to 48. Minus 24. U is 28. Minus 24 plus 28 is 4. X1 and X2 are 0. 0 is less than or equal to 4. X1 and X2 are 0. They are non-negative. U is 28. It's non-negative. So now this solution is feasible to the phase 1 linear program. By doing that one trick row operation, we were able to get a feasible solution to phase 1 linear program. Now we can apply the simplex method as we know it to get to the optimal solution to the phase 1 linear program. Okay. Good. So this solution is feasible to phase 1 LP. Apply the simplex method to solve the phase 1 linear program. Great. So from this point on, we're going to apply the simplex method as we know it to solve the phase 1 linear program. And this is something that we did in the last lecture. So we're going to go through the iterations of the simplex method relatively quickly, so I do not waste your time in this lecture all that much on this. Okay, great. So we're trying to minimize the objective function of the phase 1 linear program. For each unit of increase in x1, the objective function goes up by 1 unit. So it's not a good idea to increase x1. For each unit of increase in w1, the objective function goes up by 1 unit. So it's not a good idea to increase w1 either. But for each unit of increase in x2, the objective function goes down by 3 units. Since I'm minimizing the objective function in the phase 1 linear program, we're going to increase x2. Okay, how much can I increase x2 before I get in trouble? From constraint 1, I can increase x2 all the way to 28 over 3 before u turns negative. From constraint 2, I can increase x2 all the way to 48 divided by 4 before w2 turns negative. So from constraint 1, I can increase x2 all the way to 28 over 3 before u turns negative. From constraint 2, I can increase x2 to 48 divided by 4 before w2 turns negative. And 48 over 4 is 12. And from constraint 3, I can increase x2 all the way to 4 over 2 before w3 turns negative. And 4 over 2 is 2. So constraint 1 says you can increase x2 up to 28 over 3. Constraint 2 says you can increase x2 up to 11. Constraint 3 says you can increase x2 up to 2. So then what is the largest I can increase x2 before I get in trouble? All the way to 2. So we're going to increase x2 all the way to 2. In that case, the mean value of x2 is determined by the third constraint. Do row operations so that x2 appears only in the third constraint row. Increase x2 up to the minimum of 28 over 3, 12 plus 2. That minimum is 2. So that the mean value of x2 is determined by the third constraint row. So do row operations such that x2 appears only in constraint 2 with a quotient of 1 and nowhere else. Let's do those row operations. I want x2 to disappear from the objective function row and first and second. Now, the new value of x2 is determined by constraint 3 so that do row operations in such a way that x3 appears only in constraint 3. The new value of x2 is determined by the third constraint row, constraint 3. So do row operation such that x2 appears only in constraint 3. Okay, I want x2 to appear only in constraint 3. To get rid of x2 in the objective function row, multiply the third constraint by 3 over 2, add it to the objective function row. If I want x2 to disappear from the first constraint row, multiply the third constraint row by minus 3 over 2, add it to the first constraint row. And if I want x2 to disappear from the second constraint row, multiply the third constraint row by minus 2 and add it to the objective function row. So those are the row operations that we need to do. Okay? And we did those row operations. We saw the phase 1 in your program at the in the previous lecture. So if you do those row operations, this is the next system of equations that we reach. Just write this down. This is the next system of equations that we reach. I'm not going to waste your time to do the same row operations again. Good. What is the solution that we read from this system of linear equations? Basic variables are u, w2, and x2. So the solution that we read is u is 22, w2 is 40, and x2 is 2. And my non-basic variables are 0. My z variable is going to take value 22. Then I ask myself, did I reach the optimal solution to the phase 1 linear program? I'm minimizing the objective function in my phase 1 linear program. If I increase x1, the objective function is going to go down by minus 2. So for each unit of increase x1, the objective function of the phase 1 program is going to go down by minus 2. So it's a good idea to increase x1. Also, it's a good idea to increase w1, but maybe not as good an idea because I get bigger bang for my buck here. If I increase w3, for each unit of increase in w3, the objective function of the phase 1 linear program is going to go up by 3 over 2. Since I'm minimizing the objective function of the phase 1 linear program, it's not a good idea to increase w3. So among these two, I'm going to go ahead and increase x1 because for each unit of increase in x1, the objective function of the phase 1 linear program goes down by 2 units. That's bigger bang for my buck. Okay, let's increase x1. So the question is, how much can we increase x1 before we start getting trouble? From the first constraint, how much can I increase x1 before u starts turning negative? I can increase x1 all the way to 22 over 2. That's 11 before u turns negative. That's 11. From constraint 2, How much can I increase x1 before W2 turns negative? I can increase it all the way to 40 over 3. And that's like 13.3. So we can increase x1 all the way to 40 over 3 before W2 turns negative from the second constraint. What's happening in the third constraint? What's happening in the third constraint? In the third constraint, I'm increasing x1, but x1 appears with a negative coefficient in the third constraint. So now we know that I can increase x1 as much as I want without x2 turning negative. So this was the acute case that we discussed a few lectures ago. Okay, so the first constraint says you can increase x1 all the way to 11 before we get in trouble. Second constraint says you can increase x1 all the way to 40 over 3 before we get in trouble. The third constraint says you can increase x1 as much as you want without getting in trouble. So then we can increase x1 all the way to 11 before we get in trouble. In this case, the new value of x1 is determined by the first constraint. So we're going to do row operations such that x1 appears only in the first constraint with a coefficient of 1 and nowhere else. So we're going to increase x1 up to the minimum of 11 and 40 over 3. Minimum of these two guys, 11. So in this case, the new value of x1 is determined by the first constraint. So do row operations such that x1 appears only in the first constraint. Okay, we're increasing x1 all the way to 11. In this case, the new value of x1 is determined by the first constraint. So we do row operations such that x1 appears only in the first constraint. So then I want x1 to disappear from the objective function row. I want x1 to disappear from the objective function row. That means that I'm going to take the first constraint row, add it to the objective function row, 2 and minus 2, x1 disappears. What else? I want x1 to disappear from the second constraint row. I'm going to take the first constraint row, multiply it by minus 3 over 2, add it to the second constraint row, x1 disappears here. And likewise, I want x1 to disappear from the third constraint row, take the first constraint row, multiply it by 1/2, add it over here, so that x1 disappears from the third constraint row. Okay? And if we do those row operations, again, those are the row operations that we did in the previous lecture. The next system of equations we reach is given as follows. Here we are. What are the basic variables here? What is the solution we reach? x1 equals 11, w2 equals 7, x2 equals 30, w1, w3, and u are equal to 0, and z is equal to 0. Good. The question is, did we reach the optimal solution to the phase-1 linear program? Did we reach the optimal solution to the phase-1 linear program? Is there any decision variable that we can increase to make the objective value of the phase-1 linear program even smaller? We're minimizing the objective function of the phase-1 linear program. Is there any decision variable we can increase to make the objective value smaller? No. If you increase u by 1 unit, the objective function of the phase-1 linear program goes up by 1 unit. So there's no decision variable left that we can increase to make the objective value of the phase-1 linear program smaller. So this is the optimal solution to the phase-1 linear program. Okay. In the optimal solution to the phase-1 linear program, do we have u is equal to 0? Yes. Okay. So then let's write our final finding. The optimal solution to phase-1 linear program is x1, x2, w1, w2, w3, and u. And let me put stars here so that we're writing an optimal solution. x1 is equal to 11, x2 is equal to 13, w1 is equal to 0, w2 is equal to 7, w3 is equal to 0, and u is equal to 0. Okay, good. This is the optimal solution to phase-1 linear program. Do I have u star equals 0 in the optimal solution to the phase-1 linear program? Yes. Then it means that x1 equals 11 and x2 equals 13 must be a feasible solution to the original linear program that we would like to solve. We have u star equals 0 in the optimal solution to phase 1 linear program. Thus, the values of the x variables, x1 equals 11, x2 equals 13, must be a feasible to the origin, must be a feasible solution. Let me just say must be feasible, let me just write the whole thing. Thus, x1 equals 11, x2 equals 13 must be a feasible solution to the original linear program we want to solve. Let's check that is indeed the case. Here is the original linear program that we would like to solve. Here is the original linear program that we would like to solve. x1 is 11, x2 is 12. Is that feasible? This is 11. I'm sorry, x1 is 11, x2 is 13. x1 is 11, x2 is 13. This is 11, this is 13. 11 minus 3 times 13. 11 minus 39, it's minus 28. Minus 28 is less than or equal to minus 28. I'm good. This is 13. 13 is less than or equal to 20. I'm good. This is 11, this is 13. Minus 11 minus 13, that is minus 24. Minus 24 is less than or equal to minus 24. I'm good. x1 and x2, 11 and 13 are greater than or equal to 0. So indeed, this solution is feasible to the original linear program that we would like to solve. Okay. So this is the recap of what we did in the last lecture. This is a recap of what we did in the last lecture. Good. So now we found a feasible solution to the original linear program that we would like to solve. Now what we're going to do is we're going to solve the original linear program that we would like to solve by starting from this feasible solution. Okay? So that's what we're going to do. And how do we do that? Solving the, let's say, original linear program we want to solve, starting from the solution, x1, x2 is 11 and 13. x1 is 11, x2 and 13. So we're going to solve the original linear program that we would like to solve by starting from the solution, x1 is 11, x2 is 13. So here's a trick that we're going to see now. I show you trick number 1. Here's the trick number 2 we're going to see. When we solve the phase 1 linear program, this was the first system of linear equations that we started with. And then we applied a whole bunch of row operations on the system of linear equations. And in the last iteration, we obtained this system of linear equations. Okay? And these are the systems of linear equations that we constructed today. So I'm just pulling out the pages that we constructed today. So when we solved the phase 1 linear program, we started with this system of linear equations, and we applied a whole bunch of row operations over multiple iterations, and this was the last system of equations that we reached. In that sense, this system of equations and this system of equations are perfectly identical to each other. Okay? So that's first observation. In particular, let's just look at the constraints. These linear equations in the first system of linear equations are obtained by we do a whole bunch of row operations on the system of linear equations to obtain this system of linear equations, which means that this system of linear equations and this system of linear equations are perfectly 100% are equivalent to each other. Okay, let's emphasize that observation, emphasize that observation once more. When we solve the phase 1 linear program, this is the first system of linear equations that we started with. We applied a whole bunch of row operations over multiple iterations, and this was the last system of equations we reached. That means that Since this system of linear equations is obtained from this system of linear equations by using a whole bunch of row operations, these two systems of linear equations are perfectly 100% are equivalent to each other. Okay. In particular, let me focus on the linear equations in the constraints. This system of linear equations is obtained from this system of linear equations by doing a whole bunch of row operations on them. It means that this system of linear equations and this system of linear equations are 100% equivalent to each other. So then let me write down exactly what I said. I'm going to copy these two systems of linear equations. I'm just going to write that this one is obtained from this one by doing row operations, so they have to be equivalent to each other. That's a no-brainer. That's a simple thing to observe. So the first system, let me just focus on the constraints. That's what I need. I started from this system of linear equations, applied a whole bunch of row operations on them to apply this system of linear equations. So then this system of linear equations and this system of linear equations are equivalent to each other. Okay. We start from this system of linear equations, and through a bunch of row operations on them, we obtain this system of linear equations. X1 here, X2 here, 1 over 4 W1, 1 over 4 W1, minus 1 over 4 W1, W2 here, minus 3 over 4 W3, okay, let's make sure I did not make a typo. We seem to be okay. Okay, so what was our observation? What was our observation again? Our observation was that the system of linear equations at the bottom is obtained from the system of linear equations at the top by doing a whole bunch of row operations. Which means that this system of linear equations and this system of linear equations are perfectly 100% are equivalent to each other. Great. This system of equations, by doing a whole bunch of row operations on the system of equations, we obtain a whole bunch of row operations on the system of equations. Then these two systems are equivalent to each other. Good. So now the trick is the following. Let's imagine that I start with this system of linear equations, where u is not here, and apply the same sequence of row operations. Then I would obtain this system of equations, right? It's a mechanical argument. Don't try to be too smart about this. This is a mechanical argument. If I start from this system of linear equations and apply a whole bunch of row operations on them, I obtain this system of linear equations. If I did start from this system of equations where u's are not there, and if I apply the same row operations on them, I would obtain this system of linear equations. I would just not look at the u column anymore, do the same sequence of operations, and I would obtain this system of linear equations. So then it means that this system of equations without the u column is equivalent to this system of equations as well. Okay, so that's the first observation. This system of equations without the u column is equivalent to this system of linear equations without the u column, because by applying same row operations on this one, I would obtain this system of equations. By applying same set of row operations on this system, I would obtain this system of equations. Okay, so now these two systems of equations are perfectly identical to each other. On the other hand, if I want to solve the original linear program that I would like to solve, this system of linear equations are the system of linear equations that represents my constraints. If I want to solve the original linear program that I would like to solve, this system of linear equations are linear equations corresponding to my constraints. But these two systems of linear equations are equivalent to each other, so I might as well use these linear equations as my constraints as well. Okay, so now if I want to solve my original linear program, instead of maximizing the objective function subject to these constraints, I can maximize the objective function, same objective function, subject to these constraints, because these two systems of equations are perfectly equivalent to each other. So now let's write down what we said. Let me write it this way. So these two systems of linear equations without the u columns are equivalent to each other as well. So the two systems of equations without the u columns are equivalent. The first system without the u column, is equivalent to the constraints of the original linear program that I would like to solve. The first system without the u column is equivalent to the constraints of the original linear program that I would like to solve. But since those two systems are equivalent to each other, to solve my original linear program, I can maximize its objective function subject to the constraints in the second system of linear equations. The first system without u column gives the constraints of the LP we want to solve. So we can use the second system without the u column as the constraints of the LP we want to solve. So this is trick number two. If I want to solve my original linear program, starting from the solution that is given by the phase one linear LP, if I want to solve my original linear program by using the solution provided by the phase one linear program, I borrow the constraints of my original linear program from the last iteration from the phase one linear program. Okay, so then we can use the second system of linear equations without the u column as the constraints of the LP we want to solve. Great. So this is the second observation, second trick that we learned today. So then if I want to solve my original linear program, I can just maximize this objective function, but now subject to these constraints. I can just maximize this objective function subject to these constraints, because these two systems are equivalent to each other, and this system is just the constraints of the original LP that I would like to solve. Great. So if I want to solve my original linear program, maximize this objective subject to these constraints. Let's do that. The objective function of my original linear program is x1 plus x2. I'm going to write equals z on the right-hand side. But now for the constraints for my original LP, I'm going to borrow them from here. x1, x2. Let's write that like this, 1 over 4 w1, w2 minus 3 over 4 w3. When I'm solving the original linear program, I don't need the u variables anymore, because these systems without the u constraint are the constraints of the original linear program that I would like to solve. Equals 11. 1 over 4 w1 here, plus w2, plus 1 over 4 w3 equals 7. And x2 minus 1 over 4 w1 minus 1 over 4 w3 equals 13. And let's put z on the right-hand side. Okay. Great. So now our second trick is that when I start solving my phase one linear program, our second trick is that when when we solve our original linear program that we would like to solve, we borrow the constraints from the last iteration of the phase one linear program. Our second trick is that when we solve the original linear program that we would like to solve, we borrow the constraints from the last iteration of the phase one linear program. That's our second trick. Good. So now I want to apply the simplex method to solve this by original linear program with these constraints, this objective function. we're going to learn our last trick, the last trick of today. In this system of equations, I want to identify wx1, w2, and x2 as my basic variables. So now we're going to learn the third trick of today, and that's going to be the last trick of today. In this system of equations, I want to identify x1, w2, and x2 as my basic variables. But I'm not quite there yet. Why is that? If x1 is supposed to be basic, it's supposed to appear only in one constraint row and nowhere else, but x1 appears in the objective function row. And if I want if I want to identify x2 as a basic variable, x2 has to appear only in one constraint row with a coefficient of 1 and nowhere else, but x2 appears in the objective function row. So I got to do one special row operation again to make sure that x2 disappears from the objective function row as well. And x1 disappears from the objective function, and x2 disappears in the objective function row as well. So in this system, we want to identify x1, w2, and x2 as the basic variables, but we cannot quite yet do that because x1 and x2 appear in the objective function. Basic variables should appear only in one constraint row in different constraints with coefficients of 1. So to identify x1, w2, and x2 as basic variables, we got to make them disappear from the objective function row. Okay. So to make x1 and x2 disappear from the objective function row, what can we do? Take this constraint row, multiply by -1, add it to the objective function row, and also take this constraint row, last constraint row, multiply by -1, add it to the objective function row. In that case, x1 and x2 are going to disappear from the objective function row. Let's write down what we said. We want to identify x1 and x2 as we want to identify x1, w2, and x2 as basic variables. However, we cannot do that yet because x1 and x2 appear also in the objective function row. So then to make sure that x1 and x2 are proper these basic variables, to make sure that x1 and x2 are proper basic variables, we got to make them disappear from the objective function row. That's easy. Multiply this row by -1 added over here. Multiply this row by -1 added over here. In that case, they're going to disappear from the objective function row. Do a special row operation to make sure x1 and x2 disappear from objective function row. Okay, so multiply constraints 1 and 3 with -1 and -1 and add them to the objective function row. Great. And this is trick number 3. And this is the last trick of today. When I borrow the constraints of my original linear program from the last iteration of the phase-1 linear program, there are some decision variables that I want to identify as the basic variables, but they also may end up appearing in the constraint row. Then make sure that we do some row operations to make them disappear from the objective function. Good. Let's do these row operations. This multiplied by -1 added over here, this multiplied by -1 added over. In some sense, I'm adding these two constraints and multiplying them -1 and adding them over here. I'm adding the first constraint and the third constraint, multiplying the sum by -1, adding to the objective function, right? We're adding these two constraints, constraint 1 and constraint 3, then multiply by -1, added to the objective function. x1, 0x1, just 1x1, multiplied by -1, minus x1, plus x1, 0x1. x2, no x2, so their sum is 1x2 multiplied by -1 minus x2 plus x2, x2 goes away. 1 over 4 w1 minus 1 over 4 w1, add them up, 0 w1, multiply by -1, add on to 0 w1, 0 w1. No w2, no w2, no w2. Minus 3 over 4 w3, minus 1 over 4 w3. Add them up, minus w3. Multiply by -1 plus w3, added over here, that's going to be w3. On the right-hand side, 11 plus 13, it's 24, multiplied by -1, minus 24. In the objective function, we have minus 24. Write the constraints as they are. Great. So now, our x1, w2, and x3 look like proper basic decision variables. X1, W2, and X2 look like they're proper basic decision variables. They only appear in different constraint rows with coefficients of 1 and nowhere else. So the solution that we read is X1 is equal to 11, W2 is equal to 7, X2 is equal to 13, and W1 and W3 are 0, and Z is equal to 24. So now I'm solving my original linear program that I would like to solve by now starting from this solution. Have I reached the optimal solution to the original linear program that I would like to solve? My original linear program is a maximization problem. The objective was maximize x1 plus x2. Is there a decision variable that I can increase to make the objective value better? Yes, for each unit of increase in W2, the objective function is going to go up by 1 unit. So let's go ahead and increase W3. W3. For each unit of increase in W3, the objective function goes up by 1 unit. So let's go ahead and increase W3. How much can we increase W3? From constraint 1, W3 appears with a negative coefficient, so we can increase W3 as much as we want without x1 turning negative. Okay, what's happening in constraint 2? I can increase W3 all the way to 7 divided by 1 over 4, 28, before W2 turns negative. Can increase W3 up to 7 divided by 1 over 4, that's 28. From constraint 3, again, W3 appears with a negative coefficient in constraint 3, so I can increase W3 as much as I want without x2 turning negative. Good. So then you can do whatever you want in constraint 1, whatever you want in constraint 3. From constraint 3 and constraint 1, we can do whatever we want. In constraint 2, we can increase W3 up to 28. So we're going to increase W3 up to 28. In this case, the new value of W3 is determined by the second constraint row. We're going to do row operations such that W3 appears only in constraint 2. Let's do those row operations. I want W3 to appear only in constraint 2. If I want W3 to disappear from the objective function row, take the second constraint row, multiply by -4, add it to the objective function row. If I want W3 to disappear from the first constraint row, take the second constraint row, multiply by 3, add it to the first constraint row. And if I want W3 to disappear from the third constraint row, multiply the second constraint row by 1 and add it to the third constraint row. Let's do these row operations. Okay. This times -4 added into the first sorry, where are we? Let's be careful. Take this, we want W3, we want W3 to appear only in the second constraint row. So we're going to take the second constraint row, multiply by -4, add it to the objective function row. Okay, 0x1 times -4 is 0x1 plus 0x1, 0x1. 0x2 plus 0x2, 0x2. What is it? 1 over 4 W1 times minus 4 minus W1 plus 0 W1 minus W1. W2 times minus 4 is minus 4 W2 plus 0 W2 minus 4 W2. 1 over 4 W3 times minus 4 is minus W3 plus another W3, 0 W3. And on the right-hand side, 7 times minus 4 is minus 28, another minus 24, 28 plus 24 is 52. That's the objective function row. What else? Take the second constraint row, multiply it by 3, add it to the first constraint row so that W3 disappears in the first constraint row. No x1 plus another x1, x1. No x2, no x2, no x2. 1 over 4 W1 times 3, 3 over 4 W1, plus another 1 over 4 W1, W1. W2 times 3 is 3 W2, plus 0 W2, 3 W2. 1 over 4 W3 times 3, 3 over 4 W3, minus another 3 over 4 W3, W3 goes away. That's the whole point of doing this. 7 times 3 is 21, plus another 11, that is 32. Now let's take the second constraint row, add it to the third constraint. Let's take the second constraint row, multiply by 1, add it to the third constraint row to make sure that W3 disappears from the third constraint row. No x1 plus no x1, no x1. 0x2 times 1, 0x2 plus another x2, x2. 1 over 4 W1 times 1, 1 over 4 W1. Another minus 1 over 4 W1, W1 goes away. W2 plus another 0 W2, W2. Minus 1 over 4 W3 plus 1 over 4 W3 minus 1 over 4 W3, 0 W3. 7 plus 13, that's a 20 on the right-hand side. And lastly, we want W3 to appear in this constraint row with a coefficient of 1 and nowhere else. So let's just multiply this row across by 4 so that W3 appears in this row with a coefficient of 1. W1, 4 W2. Okay. This is this next system of equations we reach. Good. What's our basic variables? X1, W3, X2. X1 is 32. W3 is 28. X2 is 20. W1, W2 are 0. Z is equal to 52. Good. Did we reach the optimal solution to the original linear program that we would like to solve? We're maximizing the objective function in the original linear program. Increasing any one of these decision variables is going to decrease the objective function. So we reach the optimal solution to the original linear program that we would like to solve. So then the optimal solution to the original LP we want to solve is, let me write it over here rather than squeezing. X1, X2, W1, W2, W3 star. X1 is 32, X2 is 20, W1 and W2 are 0, and W3 is 28. This is the optimal solution. That's it. Okay. So then, let me show things one more time so that we remember these tricks. We learned 3 tricks today. Trick number 1. When we solve the phase 1 linear program, to get an initial feasible solution to the phase 1 linear program, you don't immediately get it, but there's a simple row operation that immediately gets you an initial feasible solution to the phase 1 linear program. What is that? We take the constraint with the most negative right-hand side, subtract it from every other constraint row, add it to the objective function row. That is the way to get an initial feasible solution to the phase 1 linear program when we solve the phase 1 linear program. So that's one trick, okay? What is the second trick? What is the second trick? when we start solving the original linear program that we would like to solve, starting from the feasible solution given by the phase-1 linear program, when we want to solve the original linear program that we would like to solve, starting from the feasible solution given by the phase-1 linear program, we borrow the constraints from the last iteration of the phase-1 linear program. When we solve the original linear program, starting from the solution provided by the phase-1 linear program, when we solve the original linear program that we would like to solve, starting from the feasible solution provided by the phase-1 linear program, we borrow the constraints from the last iteration of the phase-1 linear program. That's trick 2. So then here's my system of equations. When I solve the original linear program that I would like to solve, after borrowing the equations from the last iteration of the phase-1 linear program. And what is trick 3? Trick 3 is that I'm maximizing the objective function of the original linear program that I would like to solve after borrowing the constraints from the last iteration of the phase-1 linear program. In this case, I would like to identify x1, w2, and x2 as my basic variables. I cannot quite do that yet because x1 and x2, if x1 and x2 are going to be basic variables, they should each appear in a different constraint row with a coefficient of 1 and nowhere else. But x1 appears in the objective function row, x2 appears in the objective function row. So just do a row operation to get rid of x1 and x2 from the objective function row. Okay, for this case, what did we do? Take this row by multiply by -1, add it over here, and take this row by multiply by -1, add it on the objective function row. In that case, x1, x2 is going to disappear from the objective function row. That is the third trick. Okay, these are the 3 tricks that we learned today. Let me stop sharing my screen. Okay, so then when we put together the phase-1 per linear program, together with using the feasible solution obtained by phase-1 linear program to solve our original linear program, when we put it all together, we learned 3 tricks. Trick number 1, to get an initial solution when we solve the phase-1 linear program, there is 1 trick row operation. To get an initial solution when we solve the phase-1 linear program, there is 1 trick row operation. Take the constraint row with the most negative right-hand side, subtract it from every other constraint row, add it to the objective function row. That's trick number 1. Trick number 2, when I start solving my original linear program, starting from the feasible solution provided by the phase-1 linear program, borrow the constraints from the last iteration of the phase-1 linear program. That's trick number 2. What is trick number 3? When I start solving my original linear program, after borrowing the constraints from the last iteration of the phase-1 linear program, I maximize the objective function of my original linear program subject to the constraints that I borrowed from the last iteration of the phase-1 linear program. When I try to solve that problem, there may be some decision variables that I'm trying to identify as basic variables, but those decision variables that I want to identify as basic variables, they may appear in the they may appear in the objective function row. In that case, do 1 row operation to get rid of those decision variables from the objective function row. That is the third trick. So what is the third trick? Again, when I solve my original linear program, after borrowing the constraints from the last iteration of the phase-1 linear program, I maximize the objective function of the original linear program subject to the constraints borrowed from the last iteration of the phase-1 linear program. In that case, there might be some decision variables that I would like to identify as basic, but those basic variables may also appear in the objective function row. So do 1 row operation to get rid of these decision variables from the objective function row. Okay, good. So now this puts it all together. I can use the phase-1 linear program to find a feasible solution to a linear program that I would like to solve. And then I know how to start my simplex with that feasible solution to solve the original linear program that I would like to solve. Good. I promise you to deal with more general linear programs in this lecture, but if you do that, the video is going to get a little bit too long. Let me promise to do that at the beginning of the next video. Let's stop here with this material. That's a good wrap up. That's a good complete wrap up. Let's stop here.